Kia ora koutou, nau mai, haere mai. Welcome to lesson 5 for introductory physics. This lesson is on kinematics. So what we're going to do to start with is talk about motion graphs. We've already introduced graphs and said we expect you to know a certain amount about graphing and graph theory, but we're going to look at how graphs work in relation to simple motion, that basic motion that we talked about with displacement versus distance, speed or velocity and acceleration. We're also going to mention some of the assumptions that we make and define what we mean by mathematical models of physical systems. But the main takeaway for today, the real goal, is to understand the kinematic equations, which are for problems in one dimension with constant acceleration. So we'll build up to those. Part one is just the graphs of motion. So as I said, you already know a bunch of stuff about graphs. You know how to make a graph from data points, you know how to fit straight lines, get straight line equations from graphs, and we met interpolation and extrapolation in a previous lesson. What we're going to do now, though, is talk about creating graphs for quantities that change versus time. So if something is moving, its displacement is changing with time, and so creating a graph of that displacement versus time is a very useful way to visually see that information. Generally, whenever we do that, we always put time on the horizontal axis. Often we're looking at 2 or even 3 dimensions rather than just one-dimensional motion, but a graph by its two-dimensional nature has time as one dimension, and so therefore we can only put one spatial dimension on the graph. We can put x on the vertical axis or y on the vertical axis and time on the horizontal axis, but that means we've only represented one spatial dimension against the time dimension. We've often got 2 or 3D problems, and so in those cases, the simplest way is generally actually to just draw 2 graphs. Draw one for x against time and one for y against time. Remember that slope of a graph is rise over run. If you have x versus t on a graph, then the rise is change in x and the run is change in t. That means the slope is change in x over change in t. And we already saw that that is velocity. So the slope of a displacement versus time graph is velocity. On this graph here, we can see that it's gone up 4x units, so 4 displacement units across 6 time units. So it's got a slope of 0.67. So its velocity is 0.67 displacement units per time unit. You'll notice I haven't put units on the graph. That's because this applies to any units. It doesn't have to be meters and seconds. It could be kilometers per hour. It could be centimeters per minute. It could be anything. I haven't put units on. Obviously, when you're dealing with a real problem, you should always put units on the graph. I've left them off just to try and re-emphasize, hopefully, the fact that these equations and this theory applies to any system with any units, not just our SI units. We talked about instantaneous and average previously. Instantaneous is the velocity at a specific point, and that means the slope of the line at that specific point. If the line isn't moving, I'll just go back a slide for a moment. If the line isn't moving like that, then the instantaneous velocity and the average velocity are the same. Right? The velocity of this object is not changing at all the whole time. It's 0.67 all the way from time 0 up to time 6 units. It just does not change. So instantaneous and average are the same everywhere. But if it is changing, like the blue line shown on this graph, which you can see is curvy, that means the instantaneous velocity is constantly changing, and that means the average velocity will be different than what the instantaneous velocity is anywhere. Or it may match at some specific point, but in general. If you want to know that instantaneous velocity, then what you do is you draw a tangent to the curve. If you haven't met tangents before, do look them up, but essentially it just means a straight line that matches the curve at the exact point you want to do, that aligns with that curve, and then you just draw a straight line at the same angle as the curve is at that instant. In this case, you can see a sort of a pale purple tangent that I've drawn at time t equals 4 units. And then you look at the slope of that tangent, and that is the instantaneous velocity at that time, t equals 4 units. So in this case, actually I think the next slide has the numbers on it. The average velocity though, the average velocity is for some overall time interval. In this case, the red dotted line and the red brackets there show the values that we'll want to use for the average velocity for the time interval from t equals 0 up to t equals 11 time units. I just about said seconds, but time units. The numbers for this, we've got the average one. We're going up 9 displacement units and across 11 time units. So that's a velocity of 0.81 displacement units per time unit. The instantaneous velocity though is, if you look at that little purple line, I've drawn some extra dotted lines in there to hopefully make it easier to see that the tangent there goes up 3 spaces, 4 up to 7. And it goes across 5.5 from 1 up to 6.5 time units. So that means we've got 3 over 5.5. So the instantaneous velocity at t equals 4 is 0.55 displacement units per time unit. So you can see that the instantaneous velocity there is less than the average velocity over that entire time period. Displacement versus distance. We already talked about that in the previous lesson as well. The idea that displacement is the position relative to where you started, and distance is the total path length covered to that point in time. Distance can only get bigger while displacement can get smaller. On this graph, you can see the red line is the displacement, and you'll see that the displacement initially goes up from 0 to 4 displacement units in the first 4 seconds. I've left t off the axis there, but that's a horizontal time axis, just like usual. So we've gone up 4 displacement units in the first 4 seconds, and that means the distance has also gone up to 4 displacement units in the same time, because the distance is the same as displacement so far. However, whatever object motion this is then returns back towards the origin for 2 displacement units over the next 4 time units. But because displacement is getting smaller, distance can't be the same as the displacement. So the distance is still getting bigger. Distance is still increasing by 2 displacement units. If you've walked 2 meters back towards where you started, you've still walked 2 meters, right? So the distance is still going away from the origin. So you'll see that a distance time graph never gets smaller. It's always got a positive slope or a 0 flat, no slope. It will never go down with a negative slope, whereas displacement can. So that's hopefully enough information for you to be able to do that. I would expect you to be given a displacement graph and be able to draw the distance one. And there is an exercise like that on the worksheet. The slope will always be the same as the slope of a distance time graph will always be the same as that of a displacement time graph, except positive. So if we go back for a moment, you can see the slope here is the same. They're both positive, so they're identical. Here, the slope of the distance time is positive, while the slope of the displacement time is negative, but they're the same magnitude slope. So this is negative half, it would be. It's going down 2 across 4 time units. So negative a half, whereas the distance time will then have a slope of positive a half. And here, the slope of the displacement time is positive 1, going up 4 across 4. And so the distance time also has a slope of positive 1. The slope of the distance time graph is speed. Displacement time we said was going to be velocity, so distance time is going to give us speed. The same rules apply as we already saw for average versus instantaneous. And the same idea with velocity time graphs. I haven't drawn one because it's just the exact same idea. If we go back a few slides, imagine that that's velocity instead of distance or displacement. The velocity time graph, the slope would then be the acceleration, because rise over run, change in velocity over change in time, is how we define acceleration. Again, with velocity and speed can decrease. So speed can decrease even though it's not quite the same as displacement distance. So displacement can increase or decrease. Distance can only ever increase. Velocity can be positive or negative. Speed can only ever be positive. So here you'll see the velocity in red and the speed in blue. The speed is exactly the same magnitude as the velocity, but always positive, because speed can never be negative. Then the next thing to think about is displacement from a velocity time graph. So we're given a velocity time graph. How do we get the displacement from it? Look at the first 4 seconds on this 4 time units on this velocity time graph. You can see that in, I've called it seconds and meters in my text there, so I guess for this one we can assume it's meters and seconds, meters per second. So if the velocity is 3 meters per second for the first 4 seconds, then that means that for every one of those 4 seconds, the object has moved in the positive direction, a displacement of 3 meters. For 4 seconds, it will therefore cover 12 meters. Right? So that's fairly basic math. If it's traveling 3 meters every second and it does that for 4 seconds, it's traveled 12 meters. But that's actually the exact same thing as the area under the velocity time graph between time equals 0 and time equals 4. Right? So that rectangle that I've shaded in red there, that gives us the change in displacement. And that's true for any velocity time graph, not just straight lines, not just the one I've drawn. That's true at all times for all velocity time graphs. The shaded area, the area between the horizontal axis and the line itself is the displacement when you're looking at a velocity time graph. In the worksheet, I ask you to figure out the velocity, the displacement for this velocity time graph based on the next 5 seconds from 4 up till 9. So that's one of the exercises in the worksheet. Area below the horizontal axis, this was mentioned in the pre-math quiz, so if you've gone through that, hopefully you've refreshed yourself on this as well. But whenever you're below the time axis, or below the horizontal axis in general, the area is counted as negative area. So here you can see the red area has a displacement of 8 meters, so that's positive 8. The purple area has negative displacement of 12 meters. So the total displacement is plus 8, but then minus 12, which is minus 4 meters. So the total displacement from 0 up to 10 time units is negative 4 meters. Again, I haven't put the units on the graph, so it should really just say negative 4 displacement units. The negative displacement, remember if we were talking about distance, would still be positive because you're still traveling that far. So this isn't true for distance. For distance, you always add all the areas. It's only for displacement where the negative part is treated as a negative. Acceleration time graphs, I'm not going to, again, draw any of these for now. It's all the same rules. As we said with acceleration, we don't really differentiate between scalar and vector, so you need to remember, think about the scenario, figure out what's actually going on. The slope of an acceleration time graph is technically called the jerk. We're not going to go into that. We're not going to discuss changing acceleration. For this course, we'll only ever deal with constant acceleration. So the acceleration time graphs will always just be horizontal lines. But just like we saw with the velocity time graph, the area under the graph is the change in velocity for that time interval, exactly the same. So here's just a quick summary of all of that information. Graph of distance versus time gives the slope of speed, and the area under the graph isn't anything that we're worried about. The graph of versus time displacement is the slope velocity, and the area does actually have a meaning. It's called absment. We're not going to cover that in this course, so you don't need to worry about that either. For the speed versus time graph, the slope is the acceleration, but it's only ever the magnitude of the acceleration, because remember, speed is not a vector, it's only a scalar. So that means the change in speed is just the magnitude of the acceleration vector. The area under the graph being the change in distance. The velocity time graph that's the one that gives us the actual acceleration in terms of being a vector, because we're always talking one dimension, so plus or minus is enough information to be a vector. So the acceleration vector is given by the slope of the velocity time graph, and the area under the graph is the displacement. And finally, the acceleration, as I said, the slope is the jerk that we're not going to worry about, and the area under it is the change in velocity. The second part is the kinematic equation. So we've already talked about enough for you to know how these will all work. This is nothing new in terms of the scenarios, in terms of thinking about the systems and what's going on. What's new is just the fact that we're going to get a few equations that just help us out. So when we're doing graphs and using functions of time to represent the motion, we're always talking about instantaneous quantities, right? We're just talking instantaneous. Because especially when we've got a function of time, which is what a graph is. A graph represents a variable as a function of time. Then you can put any possible time in and get a value. And that's only possible if you're dealing with instantaneous quantities. We already know for a constant velocity. So when acceleration is 0, we already know for a constant velocity that we have the change in displacement is equal to velocity times the change in time, or indeed same with distance and speed. You'll often see me use subscript notation, which just means a little letter after the variable. In this case, something like x subscript f minus x subscript I, which just means x final minus x initial. And I just use that, it's very common, not just me, to represent those different aspects of the system without having to come up with whole new words and symbols. So when you're talking about some time interval, you might have tf minus ti, or you might just represent it as delta. That's that triangle t. And like I said, the xf minus xi, you can represent that as delta x if you want, or triangle x, change in x. When we have constant acceleration, then the velocity is changing. So we can't use those constant velocity equations that we just saw. We can't use x is equal to vt. That's not true anymore if v is changing. But what we do know is that the acceleration is changing, is a change in velocity. So if we know the acceleration, we know how much the velocity is changing, and that will allow us to figure out the displacement. So if we look at this graph, there is a vertical velocity axis and a horizontal time axis. The acceleration is the slope of this graph. That means that overall, if we start at vi, then the rise going up to vf must be equal to at, where a is the slope and t is that horizontal change in time. Because we know that the change in velocity is equal to at. That's what acceleration is. So that means that the area under this velocity time graph is our displacement, but we can figure it out in terms of the initial velocity. So you can see there we've got two separate areas that I've calculated. One is the rectangle below vi, and that area is just going to be vi times t. And the other one is this area of the triangle, which is going to be half of at times t. So at times t is just at squared. So that means the total area under this line between 0 and whatever time interval this is, t, is going to be vi times t plus a half of a times t squared. So if we know the acceleration, we know the initial velocity, and we know how long it's accelerating for, we can figure out the change in displacement that happens as a result of this acceleration. And that is one of the kinematic equations. So you can hopefully see where that comes from. It's not super critical that you can follow all of that working. It is super critical that you can understand that final equation. Delta x is equal to vit plus a half at squared. There are three more kinematic equations. The first one is just our relationship between velocity and acceleration. So final velocity is initial velocity plus a times delta t. The second equation is the one we just saw, the one we derived from the graph, where we have the final position, final displacement is equal to initial displacement plus the initial velocity times t plus a half times at squared. And there are two more there. I'm not going to show you the derivation, but they're perfectly simple to work out if you actually felt inclined to do so. But what you'll notice is that we've just rearranged the equations to get rid of one term in each. So the one that we just said, we don't have the final velocity. The final velocity is not in there. The next one, we have the final velocity, but we don't have the time now. So if we don't know the time, but we know the initial velocity, final velocity, acceleration, we can use that third equation. And the last one actually doesn't even have the acceleration in there. It's just got the initial and final velocities and the time. So again, you can get rid of whichever variable you don't care about so that you have an equation of all the ones you do. And that's important when we're doing our kinematic problem solving. So these kinematic problems are probably the category of physics problems that are closest to straight mathematics. Right? Once we know some of these variables, then we just plug in the numbers and we get a number out, and that's our answer. So it is the easiest area to forget to do the physics, to just jump straight into doing the maths. But I want you to make sure you remind yourself to do the physics, do the scenario considerations beforehand. Don't just go straight to the maths. Sit there and define your frame of reference, define your origin, figure out which way is positive, which way is negative, which coordinates you're working in, whether you're in one dimension or in two dimensions, in which case you need to have two sets of all these equations, one for each dimension and so on. And then figure out whether you're working with vectors or scalars. Have you got speed or have you got velocity? Have you got displacement or distance? Remember, acceleration is always a vector, but when you've got speed, then that gives you the magnitude of acceleration. It drops off that direction. So remember to think about all of that stuff. And finally, always make sure you convert all your values into the same units. Usually SI units, not always, but it is preferable in most circumstances to use SI units. So with all of that information, you can then approach the problem and switch to maths mode and solve that equation. When we've got gravity as our acceleration, gravity is the most common rate of acceleration in these sorts of problems, so it's one that you'll need to get used to using. But there are a few points to note. Excuse me. Firstly, gravity, the rate of acceleration due to gravity actually varies around the world. In New Zealand, it's around about 9.80 rather than 9.81, which is true for a lot of other places, especially North America, and because that's where a lot of textbooks and educators come from, that is a very commonly used value, 9.81. But in New Zealand, it is technically closer to 9.80. There is a link on the stream site to a website that allows you to find gravity at your exact coordinates using some theoretical models. So feel free to go and have a play with that if you want to check gravity in your location. Otherwise, if you're in New Zealand, use 9.80. If you're in probably Australia too, I'm not certain on that. But if you're in the Northern Hemisphere, then 9.81 is probably closer to what you need. When we have acceleration due to gravity as the acceleration for our kinematic problems, we often also write this as g rather than a, just to remind ourselves and the reader that it is gravity acceleration that we're looking at. And finally, acceleration due to gravity is not always negative. It's very common for people to just get in the habit of writing negative 9.8, right? Negative 9.8, negative 9.8 is your acceleration. But that's not always true, because remember, the positive or negative is the direction of our vector, our acceleration vector, and that depends entirely on your frame of reference. As you'll see in the worksheet, and indeed in the problem I'm about to do, the example I'm about to do, there's plenty of occasions where you want to define downwards as positive, and so then acceleration due to gravity would be positive as well. So do be careful. Again, that's part of doing the physics. Keep in mind which directions, what your frame of reference is, all of that kind of stuff. So here's my example. We're going to drop a rock off a cliff. So you'll see that's the background photo that I've used. We've got a person standing at the top of a cliff. He's going to drop a rock off, and he hears the rock hit the water 7 seconds later, according to their watch. How tall is the cliff? That's our question. First of all, and as I said, this is the bit everyone normally skips, or at least physicists tend to do in their head and never bother writing down. First thing is to define our frame of reference. This motion is only one-dimensional since there's only height change. The rock is not moving sideways at all. I'm going to call that coordinate y, which is pretty common when you're dealing with height, but there's absolutely nothing to stop you calling it d or x. You can use any coordinate symbol you want. We then need to decide whether it's upwards positive or downwards positive. I'm going to call downwards positive because I know the rock never actually goes upwards. From where it's released, it only ever falls downwards. So putting a negative in there is just going to make me write negative all the time for no real reason. And so that's purely out of laziness that I want to make downwards positive. It's just simpler for me. And finally, we need an origin. I'm going to call the position that the person lets the rock go from, that's my origin. So the rock starts at 0 and it moves downwards, which is positive, and it's accelerating as it does so according to the acceleration due to gravity, which is 9.80. So if you want to visualize this, you could imagine a giant ruler attached to the side of the cliff. The 0 is where the rock is released, and it gets positive and larger as it goes further down the cliff. So you could imagine a ruler there. Obviously, there isn't a real ruler there, but you could imagine that if you want to visualize the frame of reference. Step 2 is to write out everything we know according to that frame of reference. This might seem a bit redundant because we've been given all this information, but what we're doing is we're going through all the information we're given and making sure that we are thinking about it according to our frame of reference. So this is still part of doing the physics. It's very important to make sure that all the values and all the quantities you've got, you're thinking about relative to your frame of reference. So acceleration due to gravity, as I mentioned on a couple of slides ago, that's not always negative. In this case, in fact, it's positive because I've defined it downwards as positive, and acceleration due to gravity is making things accelerate towards Earth downwards. So the acceleration is actually positive 9.8 meters per second per second. The initial velocity is 0. Doesn't make any difference what frame of reference I chose here because it's, well, it would if the frame of reference was moving, but in terms of positive or negative being up or down, that wouldn't matter because either way, the velocity is 0 in the vertical direction. The height of the cliff is what we're looking for. So that means we're looking for change in y, which is the change in the vertical position of the rock. We know that we've just said the origin is where it starts, so that means our initial position, y subscript I, is 0. So we're looking for yf, we're looking for the final position. If we start at 0, then we're looking for the final position because that's the total change in y. And the time of the fall is given as 7 seconds. There's nothing to change here. It's already in SI units and it doesn't depend on our frame of reference. So we're just looking for a delta t of 7 seconds. And now that we've got all of that, we can do the maths. So we know the A, we know the delta t, we know the VI, and we know the YI. We're looking for YF. So all we do is we go back to our set of kinematic equations. So keep in mind that we've only got the initial velocity. We know the initial position, we're looking for final position, and we know acceleration and time. So if we go all the way back to our list of kinematic equations, and you go through here, then obviously that's that second equation, the one that we saw with the graph derivation. That second equation is the one we're looking for because it doesn't have the final velocity in it. So that's the one that we can use. And so we then just put in all the values that we have to get final height. We don't need to do any rearranging because it's already given in terms of final height. You'll notice that I've written the kinematic equation as it was originally written with x as the variable, but I then changed to y for my actual calculation because that's how I define the coordinates in my frame of reference. So our final height is 0 plus 0 times 7 plus a half times 9.8 times 7 squared, which is 240 meters. So that person is standing at the top of a 240 meter tall cliff. And the last part, very short little part here, is on mathematical models. And this is just a little bit of, there's nothing really for you to do here, just a little bit more to think about. I know we've already got lots to keep in mind as we do these problems, but just a bit more. When we write equations to represent our physical quantities, we are creating a mathematical model. Right? So that's just a term that means equations that represent our physical system. That's all it really means. For the rock falling off the cliff, we said it accelerates at 9.8 meters per second in the positive direction. So you could actually put at any time t that the position y as a function of t is a half times at squared. So remember, I'll just go back a couple of slides again. Here we had the initial position, which we set to 0, and the initial velocity we knew was 0. So these first two terms of that kinematic equation we can just get rid of because they're both 0. So we end up with the position is equal to a half at squared. Right? That's because we had initial position and initial velocity both 0. So y as a function of time is equal to half at squared, or a half times 9.8 t squared, which is 4.9 times t squared. So we can write the height of that rock as a function of time just by saying it's equal to 4.9 t squared. So is this perfect, right? Is this an exact representation of what really happens? If you use really high-tech measuring equipment and you measured the distance very accurately and precisely, would it agree with that equation? Would the rock actually follow this height equation exactly? Usually not, right? Our mathematical models are not perfect. They're theoretical, right? And there's a big difference there. We use them because they are generally pretty good, but the issue is that there can sometimes be things that make the real world vary from this model that we created. So for example, the rock, if it doesn't experience too much air resistance, and if there's not much wind to push it around, and if it gets to fall straight down, and if the person can actually release it at the exact moment that they start the stopwatch, then the model will actually be pretty good, right? It'll be all right. The rock will fall pretty closely to that, according to that model. All of those things that we've said, the ifs, those are the assumptions of this mathematical model. So any mathematical model that you make, it's going to have some assumptions, and we don't always write them down. They're often called implicit, which means unwritten or unstated. They're often implicit assumptions, but you need to be aware of them. So in this case, with the rock falling down the cliff, we have a whole bunch of assumptions, and they are no air resistance, not much wind, the rock can fall straight down, and the person manages to start the stopwatch exactly as they release the rock. So those are our assumptions. And it's very important to be aware of them, because if we did go and measure the position of that rock very precisely and accurately using some high-tech equipment and then compare it to our equation, it might not agree. And that doesn't mean that gravity is wrong, right? It doesn't mean that our model is necessarily wrong. All it means is that our model hasn't taken into account some of these things which we assumed that happen to not be true. And that's the difference between theoretical and real-world physics. In general, theoretical physics, using the models, using the mathematical models, makes quite a few assumptions. In the real world, some of those assumptions aren't true, and so we have to be aware of that so that we can allow for that in our discussion and analysis of certain scenarios. So you do need to be aware of these assumptions and when they're going to fail. The other aspect of real-world system that is missing is the idea of a boundary to the motion. The idea that y as a function of time is equal to a half at squared is great, but there's no limit given to that. I could go and put t equal to 1 billion years into that and find the displacement, and clearly that's not going to be true because the rock isn't falling for 1 billion years. So there is some kind of limit to this equation. There's some point where we can say, well, the equation is no longer true. So before the person drops the rock, so negative time, because there's nothing to say we can't have negative time, before the person drops the rock, we also don't know anything about what happened to the rock. So the equation, even though it says that it's moving beforehand, is clearly not true. And after the rock hits the water, again, clearly not true. So there's some problems with this equation, in that it seems to be telling us what the rock is doing before the person lets it go and what the rock is doing after it hits the water. And clearly those aren't going to be true. So what we could do is we could go and write new equations and say that if t is less than 0, so negative time, then we have no change in vertical position. Yt is just 0 forever before the rock is released. And then we have our equation that we already saw, y is half at squared, just for that time period between 0 and 7, while the rock is actually falling. Cool. Now the rock's only following that pattern while it's falling. And then after that's finished falling, we have a half times a7 squared, which is that 240 meters that we saw. It's just sitting at 240 meters for the rest of time, from 7 seconds onwards, forever and ever. But all that actually does, even if we wrote those out, it just introduces more assumptions. We've now got the assumption that the rock is perfectly stationary before and after the fall forever, for all eternity. And clearly that's not true either. So really what we just need to do is just think about, sorry, I've gone ahead to slide too early, is just think about what's going on and make sure that we are aware of the time frame in which these equations that we use are true. So we wouldn't actually ever bother writing out these 3 equations like I have here. We wouldn't bother. We'd just stick with our first equation of y equals, where is it? Y equals, sorry, gone back a few too many slides. There we go. Y equals a half at squared. We'd just stick with that equation. That's all we would do, but we would have this understanding from the description of the scenario that this is only true from when the rock is released until it hits the water. And if you weren't sure about whether the rock had hit the water or not yet, you'd have to go and actually check that. If someone says, oh, what's the velocity of the rock at 200 meters, you'd have to go and check, is 200 meters shorter than the cliff? Yes, it is, so I can actually use my equation. If it wasn't, if they said, what's the velocity of the rock at 300 meters? Well, that's no longer something that we can check using our models. Our equations are no longer relevant, because if it does get to 300 meters, it's now underwater, and there's going to be all sorts of other things that we're going to have to worry about. So that's the idea behind boundary conditions, just being aware. Again, we're not going to write everything down, we're not going to state it all the time, but we should be aware of where our equations are actually valid, or I should say when our equations are valid. And finally, lab physics. When you do physics experiments, what we're trying to do is set up experiments where the assumptions are very close to being true. That means that the system will behave very closely to how the model predicts, and be less like the real world scenario. So if we were going to try and do dropping the rock off a cliff in the real world, right, then there's all these other factors to control. If we go and do it in a physics lab, we can actually set up a very careful area, right, an inside space with no wind and no air, no no excess air resistance and nothing in the way of the rock and all of that. And we can use special computerized gear to release the rock and start the stopwatch all at once. We can do all of that, and then we can monitor the rate of acceleration of the rock using more high-tech monitoring equipment. And we can get the measurements very close to that y equals half AT squared using these tools to try and reduce any issues that we might have around those assumptions. The important thing to keep in mind when you're doing experimental physics is whether or not you have successfully got rid of those issues. So have you managed to get rid of all resistance? Have you managed to get rid of friction and air resistance and drag and anything else that might be an issue? And if you get results that disagree with what you expected, that doesn't mean that gravity is wrong, that gravity isn't 9.8 meters per second. It means that somewhere along the way, something about your model is no longer taking into account something that's actually happening in the lab. So there may still be some friction or some air resistance. So that's the end of this lesson. As I said, the goal here really was to understand those 4 kinematic equations and how to problem solve with them, but I did have a little bit of extra discussion around models and assumptions and things like that. But as usual, do go and practice the problem sheet. There are a number of questions on there for you to practice using those kinematic equations, but also remember to always do that frame of reference first. Define your frame of reference, figure out which way is positive, which way is negative, what your coordinate systems are, define your variables that you know, the acceleration, the velocity, the time, whatever, in terms of that frame of reference, and then switch over to math mode and solve the problem.